Welcome to Dynamic Simulation with Inventor and FEA. I'm Tristan Gunderson. A few housekeeping things before we get started. There will be a time for questions at the very end. So if you have any questions, please enter them in the Questions tab on the control panel, and we will get to those at the end. A recording of this will be sent out soon. And to get started, we're going to first start with a little bit about M2 Technologies. So M2 Technologies is a consulting firm focused on productivity, improving manufacturing process efficiency, and reducing manufacturing costs. Using generative design and best-in-class manufacturing and asset management processes, our team of industry experts can help you become more sustainable, more profitable, and more prepared to meet the demands of urbanization in a rapidly changing world. We are committed to helping clients realize the business benefits of BIM and asset management quickly and economically by facilitating the use of innovative processes and technologies, whether it's streamlining your product design, maximizing asset longevity, or optimizing your processes. Our team is one of the most experienced groups of manufacturing technology consulting professionals. We partner with world leaders such as Autodesk, Panzura, EaglePoint, and Bluebeam to utilize innovative technologies and methodologies to empower sustainable manufacturing and overcome local challenges. To support the industry, we offer a wide range of services, including BIM management, simulation, generative design, and CIO advisories. Today, we're going to be looking at FEA and simulation within Inventor. We're going to start by looking at the role FEA and simulation play in design. We'll look at an overview of the tools available within Inventor, a bit of how to select the best type of analysis for your situation, setting up and running a study, and then analyzing the results. So we'll start by looking at where simulation FEA falls into the design process. It falls in during the rapid prototyping phase. Traditional prototyping is an expensive and time-consuming process, but very important for the design process. So FEA, or finite element analysis, which is a system of replacing a physical structure with points and connections and mathematically calculating the forces or stresses across an object. And simulation using CAD replaces a bulk of the prototyping. It provides validation of designs. It highlights strengths and weaknesses. It allows you to quickly make modifications to a design study instead of having to redo a prototype. You are able to make design changes in the CAD program from what the results of your FEA is showing, and then immediately update the FEA results to get quick changes made without having to redo the design process. You also can run a wider spectrum of scenarios on a singular design than you would a prototype. If you reach a failure point with a prototype, you have to start over. Whereas with the FEA and simulation, you can always rerun a study or run a new study. And it allows you to simulate large designs without the need for scale modeling. A couple simulation tools used for enhancing communication within a company are the Inventor Studio and Tolerance Analysis. These allow for better communication between engineering and marketing, clients, and manufacturing. The Inventor Studio is a space within Inventor that allows you to create realistic renderings and animations to visualize appearance and motion. This can be used to make exploded views in order to better see internal components and how they fit together, or to simulate motion of a part in action. The tolerance analysis, on the other hand, allows you to inspect clearances and tolerance to assist in the GD&T, or geometric design and tolerancing process. It allows you to quickly determine what the best fits are in order to make sure that the part will run smoothly without increasing the cost of manufacturing by adding really strict tolerances across the board. Now, let's get more into the important simulation and FEA. A few of the tools included with Inventor are dynamic simulation, which allows you to apply joints and forces that drive motion, and you then can analyze the dynamic response of an assembly to those forces. There's then the stress analysis, which provides simulation for static and modal analyses on 3D objects. The frame analysis, which allows you to run these same studies, but on frame components which act as linear beams within the model. And then lastly, there's Nastran, which is an add-on to Inventor that comes with the product design and manufacturing collection. It works as Nastran in CAD, which is a built-in add-on to Inventor, which allows you to do the simulations that's available with the other tools with additional analysis options such as heat transfer and impact analysis. Here we can see a quick overview of some of the different analyses you're able to run using these tools. At the very start, you can see in yellow we have the dynamic simulation, which is run by the dynamic simulation tool. From there, we have the frame analysis and stress analysis, which can run a static stress analysis and modal analysis each. From there, the two in blue that were run by the stress analysis Inventor and the remaining 18 are all studies that can be performed using Nastran. This ranges from buckling to transient response, frequency response, shock response and spectrum, fatigue, and heat transfer. Now, one of the difficult things with all of these different studies is determining the right study. The important thing is to look at the outputs you are looking to determine and the input information you already have. When you open up any of the studies, it'll give a description of what it runs, but it's important to just understand what you're looking for, such as if you're looking for the motion caused by loading, then you can easily just run a dynamic simulation. However, as soon as you're looking for the stress and strain created by different forces, loads, or even temperature fluctuations or heat within a component, then you're looking at a stress analysis. There's a lot of overlap between the inputs and the outputs, so it's important to figure out which study has the right output as well as the correct inputs. Whereas, like with an impact analysis, you might think you can run it as a, it's typical, you put a force on and you get a stress out. However, if you actually run an impact analysis, you will create a velocity and impact point between objects or an object with a plane to then determine the instantaneous stress caused by that impact. So we're going to start here looking a little more in detail at these different simulations, starting with the dynamic simulation. As you can see here, one of the main components to the dynamic simulation is the inclusion of joints. When you start a dynamic simulation within an assembly, it will automatically create connections between different parts based on the constraints that were applied during the assembly. From here, you can edit these or apply additional joints in order to better create the resistances and parts that will act within the motion. Here we have the Insert Joint tab open. And if we look at the different joints available, you can see we have options for a hinge, gears, and springs included in them. Here we are going to model a spring between this simple assembly in order to see its reaction with the forces. So as we apply the joint, it'll create a visual representation of that spring on our model. We're then able to open up the settings for the spring and set stiffness, dampening, free length, and even the visual components to this, such as the number of coils and the wire and overall radius of this spring, in order to best simulate the product you will be using or what you're trying to achieve. Once you have the spring in place, all you have to do is apply a force. Now there's two types of forces you can have. You can have either a constant force, or you can have an input grapher. The input grapher will allow you to have a varied force over time. When you open it up, you'll be able to create these points in order to determine where the force will change and what it will change to. By setting this simple step graph, we're able to have the force load and unload on this spring. Once we apply this, we're able to simulate the motion that will be caused by this force. As we can see here, the simple loading and unloading will compress and decompress the spring. This allows us to quickly determine visuals of how our forces are affecting our assemblies. From here, we can either use a graphing tool to create a graphical representation of this motion or the forces involved, or we can export this to another FEA program in order to simulate the stress caused by this interaction. Now we're going to go into the frame analysis. This starts in the design toolbar within Inventor, where you have the option to insert frame components. These allow you to quickly model beams or extruded aluminum pieces with standard cross sections like I-beams. The frame components will have properties built into them, such as the moment of inertia and the bending properties, Young's modulus. And so when these are imported into the frame analysis in FEA, it is able to treat these different beam segments like simple line segments, allowing for quick and easy FEA analyses on them. However, if you have more complex 3D parts, you can use the stress analysis, which allows for the same static and modal analysis done in the frame analysis. However, instead of using simple beams, it will create a 3D mesh to define the part. Within the stress analysis tool, you're able to set up constraints such as fixed, pin, or frictionless constraints. You're able to apply loads such as a force, a pressure, a bearing load, moments, or even gravity. And then you generate that mesh using automatic mesh generation or refinement tools as needed, and then you can simulate and analyze the results from there. This workflow is very similar to that of Nastran. However, Nastran does include more tools and options for this simulation. This tool, however, is best for quick validation of mechanical and structural parts and assemblies because it is included with Inventor, and it is designed strictly for the static and modal analysis, which will allow you to see the stresses caused by forces or by vibrations at natural frequencies. Lastly, we're going to get into Nastran, which encompasses a lot of those capabilities of the previous three tools, however, also has a lot more tools and studies that you can run within it. Now, Nastran, as I mentioned, works as a standalone application or in CAD built into Inventor, where you can open it up within the model while you're running Inventor. You select from the studies to create a new analysis, from the static analysis to a spectrum response to heat transfer. You can start by creating idealizations. Idealizations replace the material properties. It works to define whether the material acts homogeneously or whether it has different material properties in different directions, such as a beam would. You can define connectors, which will set up special constraints between the parts. If you import parts directly or assemblies directly, it will apply the constraints as given, which often ends as a weld connector, which will fix their surfaces perfectly together. You, of course, can change this to slip connections, to gear connections, and allow it for parts to either pull away from each other or to move across each other. And lastly, you can set up structural members, which will work similarly to the frame analysis, where you'll be able to simplify the study by making idealizations of these structural components with a constant cross-section. Once you have all of that set, the main issue is setting your constraints and your loads. Now, constraints and loads can be placed on surfaces, edges, and vertices. The first one is setting your constraints. Constraints work as fixtures or interactions with other parts or with the mounting area that will limit its movement or resist other forces. So this can apply to where a component welds onto a larger structure, where it contacts the ground, or even just the reference point from where you're analyzing the area of interest. It's important not to put constraints too close to an area of interest if you don't have to. With the constraints, there are pins and frictionless constraints that you can apply. However, usually these will work as a perfect constraint. So the surface that is selected will not be able to move whatsoever. Whereas in the real world, there will still be minor fluctuations because nothing is perfectly rigid. So when you have a constraint too close to an area of interest, it can create non-realistic stresses. Once you have these constraints set up, though, you then want to set up your loads. Now, loads don't just mean forces. The loads can be anything from force to a moment, pressure, gravity, or even a temperature, heat, or heat flux. Now, you are also able to import loads here, such as from your dynamic simulation. These loads are going to represent any outside forces or differentials that are acting on the model. These loads will be the driving forces in the study. Once you have your loads and constraints set, it's important to define the mesh. Since this is an FEA program, it works off of a mesh where it calculates the results at the points along the mesh called nodes and with the interactions between them, which you can see on the picture as the points with the lines connecting, forming this kind of web. Now, the connections between nodes will always be a linear connection. So it can give you unrealistic results when you start getting into curves, as it will create linear representation around that curve. So the more nodes you have within a curve, the closer it will be to the actual geometry. However, as you increase your node count, it's also going to increase the number of calculations that have to happen within each iteration of the simulation. And so that's going to increase the runtime exponentially. So an important thing here is managing your node size. If you have a large uniform area that isn't going to experience much stress, there's no reason to apply a really fine mesh. You want to instead have much larger coarse mesh that will still perform exactly the same without slowing down the process. What you want to do is you want to use the mesh refinement and mesh controls in order to select the overall mesh size and the meshing within specific areas. As you can see on the side, we're looking at the teeth on a chain and sprocket. Now these teeth have very small surfaces with small radiuses. So with the general mesh applied to the object, we end up getting flattened teeth, and we're not getting the information that's necessary at that point in order to see whether we're getting any kind of shearing across these teeth. So by applying a mesh control, we can create a very fine mesh just in that select area by selecting the faces or edges. Once we do this, it will create a more detailed analysis in that area of interest without greatly increasing the node count across the entire model. After we do this, we are able to analyze the results. Nastran and the stress analysis will create a surface mapping to show the stress distribution or other information that you're looking at. Here we can see a safety factor. So with the stress analysis, our output can look at the stress, the strain, displacement, safety factor, and a few more different options. We're able to scale the area we're looking at. As you can see, the dark blue represents anything with a safety factor of 50 or above, as there is a limit put onto the scale. This allows us to quickly look at areas of importance rather than having a small point of red and everything else being solid blue. It gives us more information by limiting. Here we can see that tooth that we were looking at earlier with a von Mises stress. And so we're able to see that we're reaching a max stress of just under 240 psi, which is well within our design constraints. And lastly, we have our configurable settings. This is where we would set those min and maxes in order to narrow down the area that we're looking at, or we can even change the deformation options in order to exaggerate the deformation caused on the part more or less, or even animate those stresses or deformation as the load is applied. And lastly, we're going to look at the results from the modal analysis. As you see here, we quickly can pull up a graph that shows us the different nodes and their frequencies. You can see how with this object we are getting pockets where we're getting multiple nodes around a certain frequency and then large jumps between them. Once we have this information, we actually are able to select one of these modes and analyze the stresses at that specific frequency. So here we can see an exaggeration of the deformed part at 1600 hertz. This provides us with an estimate at the stresses that will be on this part, and we can then either modify the geometry if we are worried about this frequency being a problem, or we know to avoid motors or other objects that are likely to cause this frequency within the part. While frequency isn't something that is always looked at, this tool allows it to be very quickly analyzed and quantified based on the modal analysis, picking out those natural frequencies. All right, thank you for watching. We're now going to open it up to any questions. Again, if you have a question, on your control panel, you'll see a questions tab, and type it in there, and I will answer the questions that you have. If there aren't any questions, we will wrap it up, but I'm going to give it a couple minutes in case someone comes up with something. All right, well, I'm not seeing any questions. But if you come up with any questions later or would like to ask about any of our other services, you can always contact us at our website or at salessupport@m2t.com. Thank you so much for joining us on this webinar. A recording will be released later. We actually just had a question. Within Nastran, can we have localized mesh refinement so that we get more dense mesh near areas of interest? Yes, the mesh controls tool allows you to select specific surfaces and edges in which you can modify the mesh. So you can either reduce the mesh size on those surfaces or increase it to get a better view of those areas of interest. Thank you all for attending.